Okay, so good afternoon. So welcome to the seminar today. So today's speaker is Carnegie from CMU. So she's a first year PhD student in the machine learning department at Carnegie University, advised by Zico Kota and also Ruslan Fakirino. And one thing I should mention, she got the best paper award. Yeah.
Thank you.
So today she will be talking about controllable image generation for free with diffusion model. Okay, start.
Okay. Hello, everyone. Okay, yeah. Thank you so much for having me today. Yeah, it's been really fun visiting Tokyo. But yeah, I thought just first of all, let me just do some self-introduction. Well, mainly, I have already been introduced, but I'm currently interning at Sony Deep Generative Modeling team, which is why I am here, really. And the best paper, thank you so much, is this paper. It's basically we design a family of divergence that measures the difference that the decision makers cares. So if you guys are interested, feel free to check it out later. But today, I'm not going to talk about this. Today, I'm going to talk about generative models, which is the things that everyone loves the most right now, right? And I have done some related works in the past, but today I'm going to focus on the two papers that is about diffusion models. So, well, before we start, generative models are great. I feel like I probably don't need to convince you guys about this, but just in case, companies all over the world have been trying to develop multiple, like generative models are multiple different modalities. For example, the famous ChatGPT or GPT-4 and Stable Diffusion, which generates image from text, and also Google Music Gen, which generates music from text, which is super amazing. But basically, if we look at it statistically, or if we look at it mathematically, then generative modeling, this is just a review. Oh, by the way, I'm gonna have a review of the diffusion models and basically how it works. So if you guys are already familiar with it, I can go a little bit faster, but otherwise I'm gonna just like do a little bit of a review. So a generative model is to model the probability distribution of the data, as opposed to the discriminative model, which is modeling the conditional distribution of the label given the data. So basically why it's called generative model is because after we have this probability distribution, then we can sample from it. So for example, if we model the distribution of an image of a bedroom, then after we learn this distribution, then we can sample from it to generate new images from this P of X. All right. And there are multiple different ways to do generative modeling. So for example, the famous autoregressive models, or what we call LLM, large language modeling at this point, which is basically, yeah, super famous right now. And there are also other things like VAE, EVN, and GANs. And all of them actually share the same philosophy that basically directly sampling from the data distribution is usually quite hard because they're very high dimensional and the structure is super complicated. For example, like a real image, it's very complicated to model, especially when they're very high dimensional. Then what people like to do is they will like to first sample from a simpler, we call prior distribution. Usually it's a Gaussian. Basically, it's just like well parameterized that we know how to sample from it since Gauss. No, and then we try to transform it into the harder, the more complicated distribution. But if you look at it though, and like this just sounds like dark magic, right? It's like from noise directly to clean image. It's just like one ring to rule them all, and that's it. Like it doesn't really like it just sounds too hard, right? Even if you have some like GAN magic, it's still too hard. Oh, by the way, if you don't know what GAN is, I'm sure you do, but if you don't, just go watch this movie. It's called Catch Me If You Can, featuring Leonardo DiCaprio and Tom Hanks. Right. After you watch this movie, you'll know what it is. But anyway, one does not simply turn noise into data. It's just like too dark magic sounding. So, but if I tell you that, okay, I will transform a slightly noisy data into the clean data. That's a much, much healthier way, right? That's a much healthier type of magic, right? It sounds much more doable. So basically, what we can do is we can first add small noise to the data and record each step until it gets to the complete Gaussian noise. And then we gradually denoise from the Gaussian noise to get the clean data. And at each step, we just need to learn how to denoise that small amount of noise. Well, and that way we can sample from the Gaussian noise to the clean image, right? And ladies and gentlemen, this way we get the diffusion models. Don, you know everything about diffusion models? No, not really. But from a probability perspective, this is what you do. So basically, this is a Markov chain from the forward process, which is adding noise to the clean data, is you from x0, which is your clean image, you gradually add noise from your previous time step. And then for the backward, which is denoising, you start from your complete Gaussian noise, and then you gradually denoise from the t+1. Okay, so this is what it is. And you can train it by elbow, just like VAE. How nice. And this is what happened in 2015 when the diffusion model first came out. As you can see, this is not very good. This is the general model. This is not very good. And that's why people prefer GAN at the moment, because GAN was like way more promising. But basically, something happened in 2020. And this guy called Jonathan Ho, he just say that, oh, so we know this thing is Markov. So you just add a small amount of noise at each time step, right? So why don't we just learn a noise predictor to predict a noise and then denoise? So instead of like learning the probability distribution, which is much harder, why don't we just learn the noise? That's easy, right? So, and basically based on that philosophy, he developed a training algorithm, which is to train a noise predictor from a noisy data to predict the noise that should be denoised at that step. And then at the sampling time, it just directly reduces the noise from the noisy sample. And then you can get the clean data, like you can get a Markov chain from it. Turns out after some engineering magic, you can get very good quality image from it. So yeah, and that is what we know as DDPM. But the problem is, okay, this is a little bit small detour because this is relevant to what I'm going to talk about my work. But yeah, we need to understand like how does this work, right? How is this not dark magic? So basically, we like remember that we're still trying to model the probability distribution, right? And the majority of the models previously are trying to model P of X. And they're trying to model the P of X by maximizing the log likelihood, right? But the problem is modeling that is very hard. So for example, VAE, they use elbow, which is surrogated. It's not really direct. And then normalizing flow, you need to design very strange network architecture, which like is very limiting in terms of a bunch of applications. And then EBM, you have an intractable partition function, which is like not trackable to estimate in many cases. And autoregressive models or language modeling works quite well in some cases, but like the cases that it works well need to be able to naturally break that by the chain rule. So it works very well for language, but it doesn't necessarily work well for, say, like image, because it doesn't really have that natural order. So yeah, and also it needs to take a very long time to generate, and it cannot really generate everything at once, like all the other methods. So basically, but do we actually need to estimate P of X in order to train the model? Not really, right? Because how we usually train the model is by stochastic gradient descent with, or an ascent with maximum likelihood. So we only need the gradient of the log likelihood, right? We don't actually need the P of X if we just want to sample. we just need a gradient. So this gradient of log likelihood is called the score function. So basically what we can do is we just directly sample like randomly in the data space, and then we just go with the flow. And then we just go with the gradient, and then to do gradient descent. So say if we start here, then we just follow the arrow, which is the gradient. And then eventually we can land in some places where there's very high data density, right? So basically, what we need to do is to train a model to estimate the score function, which I'm sure you guys are familiar with. And to train the score function, you just need to maximize this L2 like distance, which is called Fisher divergence, but you don't really need to know the name. You just need to know the L2. This is so you just need to train like a score function that estimate the score. So this is very nice because it doesn't really require you to do any intractable partition function estimation. It has no unstable adversarial training like in GANs. It doesn't really need, also it doesn't really have any weird network architectures. And you don't need to break it out into chain rules, which means that you can generate everything at once. This is very nice. So what I just described, like going with the flow and stuff, is called long-driven dynamic. This is a well-known, I guess, algorithm to, And then basically what it is that you just sample from a distribution, a prior distribution that is easy to sample from, usually Gaussian, in the data space. And then you just go with the flow with some stochasticity. Yes, that's it. Okay, so this is a GIF what it will look like if you sample with long-driven dynamic. So you first start with Gaussian, and then at the end, you'll concentrate in the higher density region. All right, however, people have found that this long-driven dynamic has a lot of issues, but mainly the issue is that when the data has like very concentrated density, which it usually is, then like basically it will be very, very inaccurate. Like the score estimation here, like at the low density regions or the regions that has no support will be very, very, very inaccurate. But the problem is your initial samples, like when you sample from Gaussian, is usually gonna be in those lower density regions, which means that like at the beginning, the flow is gonna be super, super inaccurate. So say like if you start from here, then the flow like that or the long-driven dynamic is gonna guide you over here, which is not a high density region. So which means that your sample is not gonna look very realistic. And similarly, even if in high density regions, in gradient space, you can't really distinguish between this one and this one, right? Because these two are both high density regions. So the gradient will flow to both regions. So you cannot really tell the difference between these two. That's why you sample like similar density for these two regions, whereas the real data distribution will look like very different. They will have very, very different density. So basically, how do we solve these problems? Well, people literally just add noise to it. And basically what is happening is that, well, if you add noise to the data space, then the perturbed score estimation will be very, very accurate. Like the estimation of the perturbed score will be very, very accurate compared to the actual perturbed score. The problem is like, how much noise should we add, right? If we add too much noise, then it becomes super, super inaccurate. It becomes like not look like your data at all. But if you like perturb too small, then it will just not be affected. So what people do is they will first perturb very, very, very largely. And as you take the steps, as you take the gradient steps, you will try to reduce the noise that you're adding. And once you are more like certain about where you're going, you will be like once you know that you're in the data high density region, then you'll be more concentrated on where you sample from. So based on this, people have developed this is called a neo-Langevin dynamic. This is exactly what I just described. This is the algorithm, and basically you can get very nice sample from it, and with some neural network magic, you can get very comparable result to the GANs at that point. So how is it related to diffusion? Why am I like doing all of that, right? It turns out that if you take infinitesimally small steps to add noise, then it becomes a continuous time stochastic process, which is basically a stochastic differential equations. And this is generalized diffusion. So what I just described just now, like all those Langevin dynamic stuff, is actually just diffusion, right? So you can understand diffusion in that perspective. And basically you can solve SDEs with some SDE solvers. And you can also formulate it. You can also formulate the forward and the backward with the score function that we just saw. How nice. So one of the nicest thing about formulating it in the score function is that you can directly use Bayes' theorem with it. So to do conditional generation. So for example, say you want to do class condition generation. So given a class label, you want to generate the image that belongs to that class. What you can do is if you have a pre-trained, like unconditionally pre-trained diffusion model, you can directly plug a classifier to this unconditionally pre-trained diffusion model in order to generate it conditionally. This is like very, very different from what we usually see with GANs, because for GANs, you usually need to train like a separate encoder. You need to like basically collect a bunch of like pair data and then train an entirely new different generative models. Whereas here, you don't actually need to do that. All you need to do is you can pre-train this, you can pre-train the image generation part unconditionally. And then all you need to do is a discriminative model that represents which task you're doing. All right. So like basically say like now you don't want to do class label generation, class condition generation. You want to do like caption condition generation, right? So all you need to do is you don't really need to retrain this. All you need to do is you just train like an image captioning model. That's it. That's super, super simple. Yeah, and then with the score-based perspective, you can also write it this way. But here is a caveat. All right. So the score needs to be time dependent. So this is the caveat, which means that you cannot really just directly use an off-the-shelf like classifier or like image captioning, not just yet. You'll have to train your own noisy classifier, which means that the classifier that will also take into account like how much noise you have added to your clean image. Yeah, so this is like, basically these are like two different formulations of the same problem, but they all need to consider this like time or noise dependency. So controlling diffusion models is still too expensive in my opinion, all right? So even though we don't need to train in the entirely new generative model, but we still need to train something, right? So in my opinion, it's still too expensive. So I would like to ask a question is, can we control the diffusion model for free? So what we want to do is basically with a pre-trained diffusion model, can we directly apply it to some of the conditional generated tasks with no additional training, which means that we don't need to collect additional data. We don't need like a lot of GPUs to train it, and we don't yeah, and then we also don't want additional model parts because we don't want to train, right? If you have additional model parts, you probably have to train it. And also we don't want additional inference time. which means that basically we will want to keep the inference time as small as possible because that's related to the application, right? Say if you want to dynamically generate some image for some website, it will be pretty ridiculous to let your user wait for like 30 seconds to generate an image, right? You'll want it to be fast as possible. So before we ask how we do it, I think we should ask the question of like, in what ways can we control the diffusion models for free? Well, let's take the inspiration from the sampling process of the diffusion model. So in its essence, what the diffusion model is doing is actually like gradually generating images that has some noise and also some like basic silhouette of the image. And then it's basically just like generating finer and finer details, or like replacing the noise with finer and finer details until it gets to the point of clean image. So basically what I'm trying to say is that in the middle of the diffusion process, you'll actually get to see something like this, which is like a fairly noisy image, but with some like basic like geometry of the image that you want to generate. So basically the question is like, can we just directly have some like preliminary version of the image that we want to generate and then add some noise, not like the full scale noise, but add some noise to it, and then continue with the diffusion process to generate like a more realistic version of the preliminary that we provide. Well, basically, if you look at this like 2D example, what it means is that like instead of starting randomly in the data space or starting with some like random Gaussian distribution, what we do is like say like we already know what we like kind of know what we want to generate. So we'll start from here. Then basically we don't, and then we just continue with the diffusion process in the middle. Then basically highly likely, can you guys see my cursor? Like highly likely we're gonna start from here and then we're gonna go from here, right? And similarly, if we start from here, if we start from here, then we're more likely to go here. So basically this is a way to controlling like which mode in this data distribution that I am going. So instead of like randomly having the model to decide, if we already know which mode that we're going, then we just like provide a preliminary sample or like a preliminary generation as the input, and then continue with the diffusion process to get to the point that we want. So yeah, this is exactly what we're doing, actually. Super simple. And this is called SD edit. So yeah, so basically with a preliminary version of the desired generation, basically this is some like user provided guide in, if we're generating image, then it's in the image domain. So for example, in this case, it's a like stroke painting. So it's just like a very preliminary painting that shows like what's the structure of the image look like. And then you just perturb it with diffusion or SDE, whichever one you like to call it. But you don't like perturb it to the very end of the, or like very beginning of the diffusion. You perturb it from the middle. So you only add some level of noise, but not like the full scale noise. And then you just continue the diffusion from that point on. And then eventually you'll get a very, you'll get a very realistic looking image. So you may ask, oh, is this a realistic assumption for us to give the user? Like, can we ask the user to provide this preliminary version of the desired generation? Well, it turns out SD edit can be, basically SD edit reflects a lot of types of like pretty intuitive and realistic applications. So for example, especially in the image to image translation domain. So for example, we just saw the stroke painting to image generation. We can also do stroke-based editing. So for example, say here, we don't like the water. We don't want water for some reason. And we want to have forest. We want to have bushes. Then you just draw some greenish brown stuff over here, and then you can generate forest. And for example, you think the sky look too gray, you don't like cloudiness, just like all the people in Pittsburgh. By the way, my grad school is in Pittsburgh, that's why I can make that joke. But you like more Tokyo, like sunny sky, which for some reason everyone here hated, which I think is very nice. But yeah, so you like sunny sky, or like you like clear sky. So you just draw some blue over here, then you'll get a realistic looking blue sky. And similarly, say if you want to Photoshop a pair of glasses to your face, but your Photoshop skill is not that good. So you just literally copy and paste the glasses over here, and then our algorithm can generate realistic looking image of you wearing the glasses. And similarly, if you want to change hairstyles, you can also do that. Very, very easy. Okay, so yeah, so basically this is SD edit. I think it's fairly intuitive. But even with this super intuitive and easy algorithm, we actually is able to do something that GANs can never do at the time. Maybe now they're trying to catch up, but at the time that we published this paper, we compared with a bunch of like state-of-the-art at the time methods that are all GAN based, and none of them, even with like task-specific encoder trained, even their training, they still cannot really complete. They still really cannot generate images that are super realistic most of the time. So basically, we're doing something that GANs can never do. And I thought that was really cool because this was in late 2021. So stable diffusion hasn't really happened yet at the moment. So GANs still think they had a chance. Now I'm kidding, but GANs still popular now. But yeah, but yeah, I thought this is very cool that we're doing something that GANs can never do. And basically, you may have the question of, you just say intermediate steps, right? Then what step? Like there are usually like 1,000 steps in the diffusion process. So what step do you do? Do you use? Do you insert your image to, right? Well, it turns out this is more of like a realism and faithfulness trade-off problem. So basically, if you insert your input very early on, then like, for example, say if you insert your input at the beginning, which means that you're just having Gaussian noise, then that would just be unconditional generation, right? So even though you can generate very realistic image, but the image is not going to be controlled by your input whatsoever. So basically, if you start too early, then your image is going to look very realistic, but it's not very faithful to your input. Similarly, if you like start your diffusion too late, then there's not going to be enough time for the diffusion to add details to your image, which means that it's likely that like your output is going to look like your input, but it's not going to look like a real image. So basically, SD-edit will need to ask the user to find the sweet spot of like this input. And yeah, so basically you'll need to find a sweet spot of like basically where to insert your input with our algorithm. All right. So another benefit of SD-edit is that there's no model training, right? All you need to do is to have an input and have a pre-trained model, and then you just insert it in the pre-trained model, and that's it. So no training, no model architecture design needed, and no additional inference time needed compared to the original diffusion model. So yeah, so SD-edit is a free method. How nice. All right. So before I move on, is there any questions so far?
So can I ask a question?
Yes,
So suppose I want to change my hairstyle
yes, yes.
in a Japanese businessman.
Okay,
But-
okay.
Because some reason I may have some Mohican hairstyle.
Ah, I see,
How
I
can
see.
I choose the local optimum?
Okay, I see, I see. So basically, in that case, usually what you will have to do is like your input needs to be kind of reflective of what you.
Sorry, more information.
Yeah, so
That's
basically
right.
you'll probably want to like erase some of the Mohican like hairstyle. But the nice thing is that you don't actually need to have like a super good Photoshop technique. All you need to do is you just need to, for example, have a paintbrush that more or less look like the background color, and then it will be able to generate coherent background. Or you just like erase it and then apply like full scale of diffusion in that region, and it will just be like unconditional impacting in that case. So you can still do that, but basically the user will need to provide information of like this part need to be removed. Yeah.
So mathematically, the point the solution converges is determined.
It's not necessarily, it depending on which sampling technique you use. So if you use BDIM, which treats the SDE as OD, then it's deterministic. If you don't do that, then like the stochastics will come from this place, this part, but to or this part. Yeah. So it will still have some stochasticity in it. Yes. Yeah. Yeah, go ahead.
Can we align your process with like the text-based kind of generation where we can say yes
Yes.
and class is it?
Good question, which aligns with what I'm gonna say. So I'm just gonna continue if there's no more question. Great. Yes. So basically, since as is the edit, there has been many other amazing methods to try to control the diffusion models. And the most famous one is stable diffusion, which is a text to image generation model. So this is their famous example with the text from an astronaut riding a horse. They can generate an astronaut riding a horse, but very realistically. All right. So yeah, proud to say that like the stable diffusion image to image application actually use our algorithm. So basically what they do is with a preliminary like children drawing, I guess, and then you say, oh, a fantasy landscape. We want to transform this into a fantasy landscape. Ooh, a fantasy landscape trending on our station. Then with stable diffusion, it will become a very nice looking painting of a fantasy landscape trending on our station. Yeah, does this answer your question or? Okay, awesome. All right. So, but the problem is, our text input all we need? Because that seems to be what people believe in these days, right? They like a lot of artists or like AI influencers, I guess. I don't know. I have nothing against AI influencers, by the way. I think they're great. My mom read AI influencers a lot, not relevant. But anyway, a lot of people think that our text input is all we need. And all we need to do is to find the good text prompt in order to control the stable diffusion, in order to generate what we want, to have full control of what we want to generate. But is that actually true? Well, it turns out there are a lot of problems with stable diffusion based method. First of all, the stable diffusion cannot handle very nicely about the compositionality problem, which its definition, I think, comes from natural language processing. It just means that like, how do you combine the object and the attributes and the relationship between different objects? So basically the stable diffusion cannot really understand this quite well. So for example, say if I want to generate a red cube and a yellow cylinder on the table, it generates a red cube and a yellow cube on the table. And say if I want to generate a photo of a beach with a palm tree and a air balloon and a beach umbrella, well, it's not really generating any palm trees or beach umbrellas here, right? So basically, it has the problem of like either missing objects or missing the relationship between the attribute and the objects here. So, and some scholars has analyzed that this might be a clip problem. This actually might be a language problem, that the clip cannot really understand the relationship between the objects and the attribute that well. But the problem is, I think clip is still state of the art method to represent this multi-model relationship. And Stable Diffusion or Stability AI actually try to train their own clip for the Stable Diffusion generation, so which is Stable Diffusion 2. And it's to some degree, it improves the performance, but it still doesn't really solve the problem. So, and there's actually a lot more other problems that the Stable Diffusion has. For example, say if you want to generate an astronaut riding a horse on Mars on the left and a flag on the right, realistic 4K. Well, it's generating an astronaut riding a horse in the middle and a flag somewhere in the top right, top left. So basically, the Stable Diffusion doesn't really understand locations. Like it doesn't really understand the locality relationships between the objects in the scene. So so long story short, Stable Diffusion doesn't really have any like loosely speaking grounding ability. So basically, what we want to solve here is to have users to indicate where to generate what and basically only generate in the parts that the user specified. So say if we want to generate an astronaut riding a horse on the left and a pink flag on the right, then we're supposed to get some image like this, right? So this is what we want. And basically an idea is that why don't we, because, okay, let me see if because Stable Diffusion actually use cross attention to impose text condition, right? So what Stable Diffusion does, in case you guys are not familiar with it, is they first encode the condition, which is text in this case, into an embedding. And then they use a bunch of cross attention layers in the unit where Q is the image, and then K and V's are the text conditioning, and they just perform cross attention in those layers. So because they do that, so why don't we just basically only apply the corresponding text conditions to the areas where the user want the text to apply to, right? Because it's cross attention, so we can do that. Yeah, and it turns out this is exactly what we do. But before going into what we do, let's just have a reminder that like previous diffusion-based method are very costly, or either very costly or insufficient. So for example, the insufficient part is the Stable Diffusion, and the costly part are usually people need fine-tuning or designing task-specific model parts or collecting new data, or they will need like a very, very, very long like test time optimization to do that. So basically, we don't want either of these. All right. So how do we manipulate cross attention to impose text conditions in the locations that we want? It turns out it's super, super easy to do because Q is the image, right? So what we have to do is we just need to have some heuristics or some input from the user to specify literally where to generate what. So for example, say if we want to generate a dog on the left and a cat on the right on the beach, then we just specify, well, on the left, you should generate a dog, on the right, you should generate a cat. The entire scene is a beach. And then this is your image, or this is your intermediate image space. And then you'll get your key. And then basically, and then you basically aggregate each of these binary masks into a collection of masks. So far, is there any questions or comments that I can potentially answer or discuss while I'm reconnecting to the internet?
I have questions.
Yeah, go ahead.
Yeah, right now, give me the feeling that you need a lot of human engineering to edit your image to localize the position of your image.
Yes.
So
that's right.
Yeah. Then yeah, do you think it's a practical way to do that? Because compared to the automatic inference, people can just relax and see the image is generated. And now we have to draw a scratch to as a good starting point. Sometimes for me, I'm a very bad drawer. So
I see. Yeah.
Yeah.
I think this is a very valid question for SD edit actually, because SD edit actually require you to have some not like entirely okay, I think I'm back online. Okay, but like you like SD edit actually do require you to have some levels of expertise in art. Okay, are we okay? All right, awesome. Okay, yeah, it does require you to have some expertise because you want to because the shape will actually need to reflect the real shape. So I have actually tried to draw it a little bit like more weird, and sometimes you'll be able to correct it into the normal shaped data. Normal shape, I should probably look here. Okay, normal shaped oh, this is so weird. Okay, I'm just gonna look here. Normal shaped image, but sometimes it just kind of generating things that are not super realistic. So depending on which one you want, I guess, and I guess if you're like doing your generation with like better trained models such as like Stable Diffusion, these kind of things can be more or less mitigated, but not really much. So which is why we're talking about this current method, that like you don't actually need to have a lot of artistic I guess artistic expertise in this case. All you need to do is to have, well, either a bounding box or some rough shape of your object, which I think is more or less a realistic assumption to have from the user, because when the users say, oh, I want to generate something on the left or something on the right, I think usually they'll visualize the output in their mind. So they'll probably know where the object should be. And in this case, we're giving the users more control over it, which is actually the application that we have in our mind, that these things we're trying to have these things to to be applicable to real life application scenarios. Actually, like some self-advertisements as well. This may or may not happen, but we're trying to submit to the New York's Creative AI track, which is actually an art exhibition. So I'm collaborating with artists to create actual art with this method. Hopefully we can get approved. But if not, then we're just gonna have the exhibition somewhere else, I guess. But yeah, I think usually I think the users, the actual users who are going to use AI for generative art will probably want some more lower level controls other than the overall scene. Scene description. Of course, like just for fun, I think a text-based control is more appealing, but to just for fun. But I think currently Stable Diffusion cannot do it. That's why we're having this surrogated solution. But I'm going to talk about the future directions a little bit more. But I think, yeah, definitely looking into, how can we infer these type of heuristics or these type of like location informations from the text as well. Yeah. Does it answer your question?
Thank you very much. Awesome.
Thank you.
May I have one question?
Yeah, go ahead.
Okay, in that picture, the
Mhm.
dog cat is already extracted.
Mm.
How to extract dog part, cat part?
Yes, I think this is a little bit related to the previous question as well. So currently the strategy is either by human provided information or heuristics. So the heuristic is like fairly easy. So for example, like if you say something on the left, then you just select a certain region with some stochastics and stuff. Yeah.
So how accurate those parts extracted? That is what six boxes are already there.
Mhm.
But it could be enough.
Yeah, so good question. So basically it's like how accurate, like how good this method is, right, in generation. Good question. Yes, so these are the results. In general, basically the answer to the real answer to this is the performance will depend on the base method that you use. But basically we see like consistent improvement among all the base methods, like actually some cases like very huge improvements in all the base models that we use. And this is such a simple method as well. So basically, yeah. So for example, say if the location information is bounding boxes, then we can generate like something like a national and a flag. And say if the information is semantic segmentation maps, which is, oh, by the way, everything is open vocabulary. So it's like just arbitrary location, arbitrary text. So say like we want to generate a cat with blue eyes and green eyes, then yeah, you can generate a cat with blue and green eyes. Yeah, and you can see how like there's some drift in the location. And we think this is probably because of the UNet. So basically, because Stable Diffusion use UNet, and UNet has dimension reduction. So that is why when we interpolate to the lower dimensional layers, the information, like the location information, may be a little bit inaccurate in those layers. But in general, it reflects the overall like location, yeah, relationship. And yeah, and this is one that I'm particularly like. This is the OpenAI / Microsoft unicorn on a peaceful landscape with snow mountain, lake, pink cloud, and dusty sky. This is our generation. This is the one that I particularly like. And also, the regional information does not necessarily need to be object. It can also be style. So for example, here, say if we want 4 different painters or artists to draw the painting Mona Lisa, then what we can do is like, okay, Monet, you draw in this panel, Van Gogh, you draw in this panel, Picasso, draw in this panel, and Da Vinci draw in this panel, and we can get something like this to happen. So yeah, so this is like super fun to play with. And yeah, and basically it improves the localized generation ability across all the baselines. So this is Stable Diffusion 2. So basically you can see that like it's not like, because like there's no way, right, it can generate in the correct location, but like with this applied, you can see we're generating the correct, like this is carrot and this is like broccoli over here. So yeah, you're supposed to generate carrot here and broccoli here. And similarly for like these 2 methods are supposed to solve this problem really, but you can see how this one doesn't look really realistic and this one is just not accurate. So with our method applied on top of these, you can see a consistent improvement over here. And similarly with this example. And also like similar things is happening in the semantic segmentation map application. But we do notice that like semantic segmentations are finer information. So the performance is not like as good as the bounding box, but still we can see consistent improvement over the baselines. And lastly, it also improves quite a lot of the compositionality ability. So here we just use, here we don't really have human input, so we just have a heuristic of generating the first object on the left and the second object on the right. So here we want to generate a brown bird and a red sheep. And you can see that like none of the baselines is generating things correctly. They either miss object or they just like kind of just like mess up the attributes. And our method can generate very realistic images with the correct relationship. And similarly for the other example. Yeah. And a very nice thing about this method is that it doesn't really require anything, does it? Like, oh, I mean, it requires human input, which in some cases may or may not be the like a hurdle, but it doesn't require training, which means that there's no like data collections. There's no GPU well there you need one GPU because you need stable diffusion, but you don't need like 12 GPUs or 16 GPUs. And yeah, and then you don't need to design anything. You just copy and paste the 5 lines of code that I wrote into your model and you can do it. And also it does not only, well, I'm gonna talk about that later, but it does not only work for stable diffusion. It actually works for anything that has cross attention in it because it's just a generic thing for cross attention. This is very nice. And also, remember the realism phase one is trade-off. Well, basically, it turns out that we do also improve that trade-off, and we do not increase inference time. So basically, what you need to compare is the boxed numbers. So basically, we compare to the baselines, we either decreased the inference time or we don't change it that much. So this is very nice. And yeah, just like I mentioned, it can be applied to anything, not only diffusions, but GANs or autoregressive like transformer based model. Very nice. Yeah, but and that's it for my talk. Yeah, if you guys have any questions, feel free to contact me. This is my email. This is my website. Also, please follow me on Twitter because apparently Twitter followers is very important these days. Oh, X. Yeah, sorry. X followers is very important these days. But yeah, if you guys have any questions, feel free to ask me right now or yeah, contact me later. Thank you so much.
Yeah, thank you very much. Yutong?
Yes, of course.
When I use the diffusion model to generate multiple same objects,
Yes.
I feel that the appearance of each object
Of course.
becomes very low quality.
Yes.
Do you think this is because the text input the problem, or like I want to use diffusion model to generate 7 people, then can I use this CAC method to guide the generation?
Yes. This is actually one of my previous like inspiration of why I did this model or why I did this application is because I realized that stable diffusion cannot handle numbers. Like the numbers is not very good. It's not very good at like figuring out numbers. So that's why I thought, okay, so what is the easiest way that we can solve this problem? Well, probably to spatially separate each one. So yeah, it can actually, I don't have examples over here, but in COCO data, so we experiment on COCO dataset, and in COCO data, it has like examples like 3 teddy bears lying on the bed and stuff, and we can do better than the baseline. Yeah, but like, yeah, just to emphasize though that like our method is better than the baseline, but like based on the base model performance, it's still like there's still like basically you can get better result than the others depending on the base model. Yeah. Yeah.
So I'm not stable diffusion, but mid-journey and I try to write the straight line. Then lower left corner to upper right corner, just straight line, but I couldn't. So
Oh,
that kind of very simple structure, like just a straight line or a regular triangle, I couldn't.
oh,
Is that the original that kind of simple image or the if there a reason we could.
interesting. I didn't know this. Was the base model Imagen or like what is the base model again?
The basement, I don't know the basement model, but mid-journey is maybe.
Oh, mid-journey. Okay. Yeah, I see. Okay. Oh, yeah. We don't really know what they use, but I guess they would fusion. I think okay, interesting. I did not know this problem, but I hypothesize it's probably because the data set that they trained on doesn't include examples like that. But yeah, and that is a very interesting problem though. Yeah. Right. Yes, of course. Oh, this is yeah, thank you so much for mentioning this. I did not know this. I will do more investigation on basic geometry generation problem. Yeah.
I also have a question here.
Yeah.
So what happens if you consider any object that is more like, logically constrained? Maybe the text is clearly one example. If you can simply randomly change some parts, but or the logical relations are somewhat important.
I see. So this is this is actually I guess either a benefit or a drawback depending on what you would. Oh, this is also kind of tied into the future works that we're thinking of. But this is either like a drawback or a good thing, I guess, about the model. So for example, you see how this case in this example, this doesn't really look logical, right? Because the bird is the same size as the sheep. But that is what our heuristics say. So our heuristic actually specify like two same size rectangles to generate these two objects. So basically, I guess depending on how much control you have, so this is kind of like tied into the realism faithfulness trade-off. So basically, if you want more control, then it will probably not really follow the prior that you learned in stable diffusion, which means that a lot of the relationship between the object may break. But so for example, here, SD 2.1 that actually plus our method doesn't really have that much control, but it has a much more logical generation. Whereas here, you have more control, but the relationship is not very logical anymore. So what we are thinking what we're thinking next is to also solve some of the problem from previously is that like, can we sort of like have a better heuristics than to the left to the right? Can we have a better, basically, can we either learn or like infer these type of heuristics from say like large language models? So basically, like say we have a caption that has some like location information in the caption. Can we like if we provide some like a few pairs of the caption and the bounding box coordinate, can we just use like GPT-3 to generate like logical bounding box?
This is called prompt engineering.
Yeah, this goes back to prompt engineering, unfortunately, but I feel like I feel like something simple like this can potentially work. Yeah, but so far it's really depending on like it's still a trade-off. Basically, like if you want more control, then it's gonna ignore the logic learned in the prior more. But if you want the prior more, then you won't have as much control. Yeah.
Thank you.
Yeah.
And any question from online?
Can I have a question?
Yes.
So I'm wondering if it is possible to generalize the idea of CAC to generate a more detailed or delicate structures like the posture of characters or the position of arms, legs, or even fingers. So it's more detailed. Is it possible to use this kind of CAC method?
Yeah, so basically, yeah, this cat example is one of the examples, I guess. So like, yeah, I was thinking that like so basically you can like separately specify the the different like text descriptions for different parts or like different attributes of this cat. But again, I feel like when you start to like have very fine-grained information, then you started to need some kind of artistic expertise, because the location need to somehow reflect the your reality a little bit. Otherwise, it will either be going back to the previous question, it'll either be like not accurate or not logical, basically. So yeah, but yeah, I think that's possible.
Okay, thank you very much.
Other questions? Okay, otherwise, let's thank Kelly again for the great talk.
Thank you.